Today, it is very much an honor to provide this webinar with George Wiley. This is the second of the three camera webinars we have for this week, and this will be following what we presented on Monday with Raj Kumar, focusing on the CSI-2 over D-PHY imaging conduit solutions. Right. So Mipi Alliance, it's a global collaborative organization founded in 2023, comprising around 400 members, and we continue to advance solutions, interface solutions, standardized interface solutions for mobile and certainly beyond mobile product platforms. Our mission is to provide hardware software interface specification device vendors need to create state-of-the-art innovative devices and accelerating time to market solutions and reducing cost. In the multimedia specification, our focus will be on the CSI-2 camera solutions in this webinar. The CSI to frame format, zooming out, it has been incredibly successful for over the last couple of decades, and a lot of this has to do with three important pillars coming together, including a close partnership and alignment between the sensor companies and application processor companies under the umbrella of Mipi to help define a highly optimal and a curated protocol and a frame format required for a broad range of camera and imaging applications. Second is the low energy PHY transport, comprising highly comprehensive solutions on the transmitter for the receiver and certainly the channel. And in this webinar, we will be focusing on the C-PHY transport solution. And third is our ability to come together as a collective and help define the various emerging applications and ensuring we are able to author and define the provisions required for the applications before the time to market, in order to meet the time to market requirements. Right. So just a quick recap of the CSI to frame format. It is comprised of the packet header, which we often refer to as the mission critical content, comprising data types, virtual channels, and when we discuss the D-PHY, the packet header has a error checking mechanism. For C-PHY, and we will go further into the details, the packet header is going to be replicated twice with a PHY generated and consumed control code in the middle. What's in the magenta are the dynamic long packets, which is used to transport pixel data, and it is considered as best effort transport coupled with CRC. And embedded data may contain content that is beneficial for softwares and drivers. We should also note that there are a number of complementary specifications supporting CSI-2, such as the PHY transport layer solutions, including A-PHY, C-PHY, D-PHY, and I3C. Camera service extensions comprising functional safety and security. Provisions for unified imaging software drivers using camera command sets and Disco for imaging, and the conformance test suite. So with the first mover advantage spanning over a couple of decades, we do see expansion of the Mipi CSI-2 imaging conduits for mobile consumer-based platforms, but certainly also expanding to a number of commercial and infrastructure imaging and vision systems as well. So some of the key core features are illustrated in this slide. As we presented on the Monday's webinar, PST is the power spectral density reduction that is supported by Mipi CSI-2. And for the CSI-2 over D-Phi, the Galois field 2 to the 16 polynomial applies to the data lanes. For CSI-2 over C-Phi, the scrambling solution would apply to the entirety of the link, mainly because the C-Phi is an embedded clock and data. On Monday's webinar, we also clarified there's an emerging D-Phi ECM, which would also be an embedded clock and data, which may benefit from the link-based PST reduction that is offered by scrambling. LRT stands for latency reduction transport efficiency. It has two underlying features that come together, including a PDQ and ALP, which we will also elaborate today on how the LRT maps to CSI-2 over C-Phi transport solutions. USL, it's a phase 1 solution that we currently have that has been adopted. Phase 2 is presently work in process. That is the solution to help reduce the wire count between camera modules and the application processor, leveraging on all the goodness that LRT supports. We have the smart region of interest solutions as well, and we will elaborate in detail the two flavors of smart region of interest solutions that was developed over a couple of specification revisions. So phase 2 is essentially it was an update that was made after the phase 1 features were introduced. The DPCM and MPC are the compression solutions, where on Monday we provided the details of how a multi-pixel compression 10:5 it is able to deliver superior image quality of around 14 dB, a peak signal to noise ratio over the prior DPCM 10:6 compression, which contains again the 20% compression of efficiency in addition to the 14 dB PSNR advantage. And this was qualified over various difficult, challenging scenes and modular transfer function, frequency response, spanning high intensity, medium intensity, low intensity, crossed with high, medium, low contrast images. And the last box on the bottom right-hand side are the two provisions that we have for manifesting unified imaging drivers, help accelerate sensor bring up with tuning and calibration, are the camera command set and Disco for imaging. So always on Sentinel Conduit, it is an ultra low power, low energy consuming interface solution, and it is to help support always on sensors typically operating with low frame rate, low resolutions, compared to solutions that may be coupled to the high performance C-PHY and D-PHYs. AOSC uses I3C, SDR, DDR, and the HDR BT, which stands for bulk transport, as either a single lane or multi-lane configurations to help transport CSI to frames and controls. The VDSP, the Vision Digital Signal Processor, it is an I3C host controller, and the SNS or the sensor is the I3C target. The supported operations include AOSC. So these are the highly efficient CSI to frames and the shadow register updates for 3A, for periodic 3A updates. So that's the AOSC transfer over I3C. Or second flavor could be simultaneous AOSC transfer over I3C coupled with either C-PHY or D-PHY transport for a higher resolution, high fidelity frames. And the third mode could be switching between AOSC transfer over I3C for low power inferencing And if some interesting event is detected, then the system could switch the sensor to capturing full frame and transport the high resolution, high fidelity frames over C-PHY or D-PHY. Introduction of AOSC enables Mipi CSI to transport over the low cost, uh, far less complex 2-wire I3C GPIOs without the need for the sophisticated PHY transport solutions, albeit the I3Cs provide substantially reduced and lower bandwidth. In this, from a bandwidth perspective, if we look at some of the example configurations, such as QVGA at 10 frames per second using raw 10, that results in about 8.5 megabits per second, which can be supported by a single lane, and this is a 2-pin GPIO, data rate comprising around 11 megabit per second effective bandwidth. The 720p at 10 FPS using raw 8, requiring 81 megabits per second, can be supported by the 4-lane high data bulk transport, around 95 megabits per second. There are two modes within AOSC, and one of the popular modes is the optimal transport mode operation. And in this illustration, what we see is a sequence of operations, or a possible sequence of operations. The VDSP, again, is the Vision Digital Signal Processor, SNS is the sensor, SDA is the data line, and SCL is the clock line. So everything starts by once the sensor is programmed using the existing CCI commands over I3C, everything starts with an optional on-demand frame that's represented by ODF to commence initiating the sensor exposures. Now, the reason it is in a dotted box, and the reason it's in a dotted box is to indicate that it is actually optional. The sensor could also be configured as a continuous frame transport. And if it is continuously streaming, and there are some applications that could benefit from that, then ODF simply will not be required. IBI is the in-band interrupt. It is generated by the sensor at the beginning of an image frame. So at a high level, from a high level conceptual perspective, we envision the sensor to have a circular buffer. The long packets corresponding to the pixels are written into the circular buffer. Once the circular buffer reaches a certain threshold, the IBI is initiated, which would then enable the VDSP to start reading the contents in the circular buffer, which essentially are the CSI-2 long packets. Right, so when the IBI is initiated, the VDSP may optionally enter into a higher data rate mode, depending on how this sensor is configured, and that will, at a system level, map to an optimal I3C data rate. And the TPP is initiated by the VDSP to read the payloads corresponding to the frame. These are labeled as LPP1 all the way to LPPN. But from a formatting perspective, these are essentially the long packet, the CSI-2 long packet payloads. Interconnect synchronous padding bytes may be appended to select long packets, and that is to compensate for the fact that the clocks may not, the read clock rate may not necessarily match the circular buffer or the FIFO rate within the sensor. So to mitigate that, the link will always be running at a slightly faster rate, and the system is configured in such a way that synchronous padding bytes may be inserted. Of course, from the VDSP perspective, we will know the length of the payload as it's a VDSP that would have configured the frame configurations. The CRC is unlike the CSI to transport. CRC here is optional. Again, this was made optional purely from the perspective of if you're looking at every single opportunity to save even like fraction of a picojoule of energy, considering these systems are considered to be always running, and optimal energy consumption, reducing power was of a high priority. The XHDR it's essentially the opposite of the EHDR. Here, the VDSP it enables the VDSP to exit the high data rate mode. So next, we are transitioning to another important feature. This is the smart region of interest. Smart region of interest. The first one was introduced in the phase 1 was introduced in CSI-2 version 3.0, and phase 2 was introduced in CSI-2 version 4.0. So the CSI-2 4.0 SROI it builds on what was developed in CSI-2 version 3.0 SROI phase 1. Extending imaging systems support to including the companion vision digital signal processor, inferencing solution for platform integrators, with the support for external SROI in addition to the integrated SROI that was previously introduced. And again, the introduction of the external SROI enables imaging system deployments to utilize the baseline non-smart sensors, or perhaps even the legacy sensors that do not have that inferencing capability, coupled with this VDSP, the companion VDSP solution, to help support varying classes of inferencing solutions. So the way the SROI works, it's intended to facilitate certain object recognitions at the periphery, at the edges, and it can, from a system perspective, help reduce the bandwidth energy consumption by selectively transmitting the interesting regions of interest. And those are carved out from the original frames in the sensor. So the integrated SROI as a smart sensor may have a multi-stack solution that facilitates this inferencing, and the external SROI will have the companion VDSP facilitating these ROI extractions. It should be noted the CSI-2 over C-PHY, these are the ones that's already adopted, and the IP is available today with sensors. These are with the legacy error checking and correction, they are supporting 4 virtual channels, which means at most we can transport 4 regions of interest coupled to VCs. The CSI-2 over C-PHY with the enhanced ECC, in which 2 bits were salvaged from the error checking and correction algorithm, for those solutions, we could support 16 virtual channels. And I should clarify, these are the C-PHY FCM transport solutions that exist today. And the third is with C-PHY, which we are going to cover today, this CSI-2 over C-PHY solution, we can support up to 32 regions of interest with the 32 virtual channels. It should also be noted the packet header for CSI-2 over C-PHY has a series of reserved bits which we are not using, and perhaps some implementers use them to extend the virtual channels to support beyond 32 virtual channels, which means there may be a possibility to support beyond 32 SROIs. Right. Right, Mipi CSI-2, there's presently Mipi CSI-2 imaging systems using D-PHY FCM differential signaling solutions, as indicated in the illustration above, and the C-PHY 16 bits over 7 symbol ternary signaling solution deployed across multiple classes of product platforms, as illustrated below, using 3 wires. The CSI-2 over D-PHY FCM supports a variable link rate aligned with the image sensor pixel clock. The data is transferred via differential data lanes, which are sampled at the rising edge and falling edge of the forwarded differential clock. This is what we covered on Monday with Raj Kumar. The CSI-2 over C-PHY also supports variable link rate, where the clock is recovered from the ternary symbol transitions over 3 wires. The CSI-2 over C-PHY offers an effective bandwidth coding gain of around 2.28 by transporting 16 bits over 7 symbols. This is the coding solution that's already deployed on imaging platforms today. In today's webinar, George will also be discussing the emerging 3-wire CSI-2 over C-PHY 32 bits over 9 symbol signaling solution that's presently under development. Some image sensors may also support combo C-PHY D-PHY signaling, since the pins are considered to be electrically compatible. And again, we find the CSI-2 over C-PHY D-PHY imaging conduit solutions are relatively well established in the broader ecosystem, supporting multiple applications. So that said, I would like to invite George on the stage to present the overview of Mipi C-PHY with the present 16B7 as ternary signaling solution.
Hello. Okay, so I'll run through a brief description of the version history of C-PHY. So it began, let's see, back maybe almost 10 years ago, 9 years ago, with version 1.0. And you'll notice at the top of the chart, there's it's showing for the progressive versions of C-PHY up to version 2.1, which is the release version today. The first row shows the symbol rates and the data rates that are possible for each version. So the symbol rate, which, as Harold mentioned, there's a coding factor that's used. So the symbol rate is actually lower than the bit rate capability. So the bit rate capability in parentheses is the number of bits per second, gigabits per second, that can be passed through the channel per lane, per 3 wires. So it began with in version 2.1, for instance, with the standard channel at 2.8 gigasymbols per second, which provides 6.4 gigabits per second per trio, per lane. Up to today's version, which is provides up to about 13.7 gigabits per second per lane. Also, it's showing a standard channel and a short channel. There are actually 3 channel definitions within the C-PHY spec. Actually, the channel definitions in the C-PHY spec and the D-PHY spec are the same channels. So with the shorter channel, it's possible to have an even higher symbol rate and bit rate capability, just due to the smaller amount of loss on the short channel. So over time, we added a number of features, as you can see, to probably on the top of the list here is increasing the rate, the throughput. Over time, so we began by adding a basic pre-emphasis feature in the transmitter, followed on by an advanced TX equalization capability. So this is kind of similar to pre-emphasis, de-emphasis, but it's been customized for the C-PHY encoding, which we'll look at in a moment. And then finally, in version 2.0, then we added our RX equalization. It's a continuous time linear equalizer, a CTLE capability in the receiver to achieve even the higher rates. And so those are the technologies that enable the higher bit rates that we see in the symbol rate rows at the top of the chart. There have been some other interesting capabilities, the unterminated mode, and particularly the reduced amplitude mode. With reduced amplitude, of course, the throughput is a little bit less, but the power consumption is less, and it can use exactly the same power supply rail that's used by the D-PHY standard. Coming in at version 1.2, there was an alternate low power mode capability that was added. What this does is it replaces the PHY LP mode, the traditional low power mode, with the capability to so that the PHY can remain completely in the high speed mode all of the time. Doesn't need to do the switching back and forth between the high speed and the LP mode, and that's what the alternate low power mode enables. Then other enhanced functions, we increased the width of the PPI. This is the PHY protocol interface. So this is the interface between the PHY, which is in the pad ring, and the protocol logic, which is usually in the core logic of an IC. So running at a higher bit rate, then it's really necessary to increase the width of the data path between the PHY and the protocol layer, so that the clock doesn't run at an extremely high speed between the PHY and the protocol logic. We also added a high-speed reverse mode for enabling some interesting CSI-2 features, and also the capability to select sync words, which really improves the performance of the scrambler, so that there's no periodic, very, very little periodic signaling that appears in the data channel. The fast lane turnaround enables the PHY to turn around very quickly in support of the high-speed reverse mode, and then also there was an IoT a 4-meter channel support then that was added. That capability is mentioned in the spec and describes how that can be achieved. Okay, let's go to the next slide. Thanks. Okay, so this slide describes maybe the somewhat unusual signaling technique that's used by C-PHY. So we'll start at the upper left and kind of rotate around counterclockwise to the other side through the figures. So similar to the rotation that's used in C-PHY, we'll rotate through the figures. So the first upper left shows the low-level PHY drivers and how the lines are driven. So rather than having a differential pair, there are actually three signals that work in tandem. And so these are controlled with very high-speed logic within the PHY, just as the conventional differential interface is driven. And there are actually 6 possible states that can appear on the 3 wires. So there can be each signal can be driven at a high level, a mid-level, or a low level. And in this figure, we can see that A is at a high, B is at a low, and C is at a medium level. There's also a rule that's so you would say, well, hey, I can actually have, there are 3 wires and there are 3 states, so I can have 3 to the 3rd power levels. But there's actually a constraint that creates a lot of kind of magic in the way C-PHY operates. There is the requirement that each wire is at a different state always. So if one line is at high, then the other 2 lines need to be at either low or medium. And you can see here, then the signal is transmitted in, you can kind of think of this as in a single-ended form, and it's received with a true differential receiver, actually 3 low-power differential receivers. So one looking at A minus B, the other, the middle looking at B minus C, and the third receiver looking at C minus A. Okay, so now we'll step down to the lower diagram, and we can actually observe what I was saying. How during each time epoch, we call that a unit interval, a UI. How each wire is driven to a different level, and you can see the timing diagram that has the red, purple, and green waveforms superimposed on top of each other. How the level on each line is different. And notice that also there's another encoding rule, that there is always a change at every time epoch, at every unit interval. And this is the way that actually the clocking is encoded within a signal trio, so that we're actually embedding the clock. Now, what that means is, of the 6 possible states that exist, it's only possible to really utilize 5 states. So there are 5 different states. So you're in one interval, we're occupying 1 state, and it's possible to transition to 5 other states. So the possible amount of information that we can encode then would, of course, be log 2 of 5. So this has about roughly a 2.32 bit per symbol. So it's maybe a little bit interesting to get your head around how can we transmit this fractional number of bits per symbol. So we'll move on to that. By the way, that what we do is we actually gather up 16 bits, and we can encode that into 7 symbols using a rather unique mapping mechanism that's actually very easy to implement in digital logic. So we can actually recover about 2.285 bits per symbol out of the theoretical 2.32. So we do actually lose a fraction of a bit per epoch, just due to the implementation compared to theory. But we are actually able to then to use those somewhat unused, that unused a little bit amount of information to be able to transmit special code words through the channel, which is actually very beneficial for the operation of C-PHY, and also supports some advanced features of CSI-2. Okay, so moving to the right, we can show. So we actually send within a link. So a camera, for instance, a camera communicating with an SoC system on chip would then probably, in many cases, it may use 3 lanes operating in tandem. So just as in a D-PHY link, we would have 4 data lanes and 1 clock lane. Well, C-PHY, then we would have 3 data lanes operating, three lanes operating in tandem. And also note that the clock is encoded within each of those 3 lanes. So the clocking is actually independent. So we can tolerate quite a large amount of skew between the C-PHY lanes in this case. Moving up to the multicolored figure above, showing the layers that exist within the C-PHY implementation and supporting CSI-2. So at the very bottom, there's the channel, which is the kind of the coax that's shown on the upper left picture. Next, we have some encoding and decoding. So this is responsible for taking converting the actual symbol data. So a symbol is one of five states, and we encode that into the actual levels. So the high, mid, and low levels that appear on the link. And as I mentioned, we collect 16 bits and convert that into 7 symbols. So we then have a 7-symbol group. So there's a simple parallel to serial, serial to parallel conversion that's done on the symbol data. And then finally, up one layer higher is a mapping function. So that mapping function receives 16 bits and then converts that into 7 symbols. So it seems a bit it may seem at this level to be a bit complicated, but actually the encoding and the mapping functions are very simple, and implementations are provided. Example implementations are provided in the spec. So, and I always say to a person it seems complicated, but to actually implement this in logic is very simple. And then finally, the PHY, the purple, the mapping layer, the data is passed to the CSI-2 protocol layer. So why do this this translation between bits and symbols? So one thing is that there are actually a lot of benefits that are, and those benefits are available both for high performance applications, and as well, it's very beneficial for even the value tier of devices. So one thing, we can achieve a high bit rate easily through this the 2.28 times encoding factor. So what that means is the bit rate can be 2.28 times the channel rate, or we can think of the channel toggle rate is actually rather low compared to the throughput. So that's clearly an advantage for emissions, for power consumption. As I mentioned, the next bullet is lower power consumption. The receivers can be biased with the bias currents in the analog front ends of the receivers can be low because of the lower symbol rate, the lower toggle rate of operation. There's not a clock present here, so there are no emissions from the clock lane that can be a jammer to a high-speed communications receiver in a device like a mobile phone. There also are few lanes are required because of this encoding, right? And that so that can be manifested in either having fewer lanes or even further reducing the toggle rate. Also, in an implementation, there's a flexibility now to assign lanes to a specific camera. So when we have an SoC that might support multiple links, it's possible then to dynamically assign these lanes to different links. So we might have one link that has maybe one lane or two lanes, and another link that could be, maybe could borrow a C-PHY lane from another link that could have maybe three or four lanes, three or four trios. So that provides a great amount of flexibility. So as far as the ecosystem goes, the C-PHY and D-PHY, as Aaron mentioned, they can be multiplexed onto the same device pins. And in fact, C-PHY was kind of created in the same light as D-PHY. So the LP mode is exactly the same. Many things are in common. In fact, even it even goes so far as to have the section and subsection numbers in the two specifications are nearly identical. The PHY protocol interface is very similar, and as well, the conformance test suite for both standards has very similar structure. C-PHY doesn't have the clock lane tests in those groups, but otherwise the two are very similar. So they're kind of like two PHYs maybe in the same family that have very much in common, and they're both kind of inherited from the same place. So that's a maybe a not so brief summary of the basic parts of C-PHY, and coming up in a little bit we'll talk about what's coming up in the future. Okay, thanks.
Thank you, George. That was incredibly informative. I almost feel like this slide in itself is a fantastic reference for as a primer for C-PHY. Very well said, George. So when George brought forward this brilliant idea of reducing the overall system energy using 3 wires, and the prior solution, as George mentioned, was a C-PHY, CSI-2 over D-PHY, and we have the C-PHY. From a protocol perspective, we were confronting one fundamental challenge, and that was how do we mitigate the Gaussian errors? As a differential signaling, there's a 1-to-1 correlation. But as George mentioned earlier, when we are transporting 16 bits over 7 symbols, there may be some interdependencies. So after various imaging system analysis and looking at the various applications, the solution the group derived is as depicted here. Here, a 3-lane example is shown, in which the packet header is replicated as illustrated as PH, and between the packet header we have a sync code. And the sync code is a C-PHY generated and consumed control code. And there's a lot of thought that actually went behind this particular architectural solution. And what is depicted on the right are some of the worst possible scenarios of errors manifesting. So from a very high level, after much prognostication, what we find is that the worst possible location for the error to strike is going to be the last symbol of the first packet header. Because what that means is that it not only corrupts the first packet header, but there is a chance that it may end up corrupting the sync word and the subsequent packet header and whatever may come afterwards. So from that perspective, we have provided here a single lightning bolt, dual lightning bolt, 3 lightning bolt examples mapped to loss of no symbol clocks, loss of 1 symbol clock, and loss of 2 symbol clocks, and how the system is able to recover by defining the RX detection as a don't care followed by the 5 4s followed by 3 definition of the sync word. So just by ignoring the first symbol, the system is able to recover quite rapidly. And this replication, I think we can safely say it is incredibly robust across broad range of imaging and vision applications. As George also noted earlier, another incredibly important imaging system architectural advantage with that C-PHY has brought forward, and these are sensors available today and systems available today, is the ability for the SoC to be not locked into frozen pin ports for D-PHY, CSI-2 or D-PHY forwarded clock mode solutions. So in this illustration, there's an SoC using D-PHY FCM. It's an 18-pin SoC, and that is mapped to a by 4 by 1 by 1. And through the development and lifespan of the SoC, should the camera configuration, should there be a need to change the camera configurations from, based on some changing or emerging application, then the ability to make those changes are somewhat challenging, mainly because at the SoC level, the clock pins mapped to the FCM solutions are quite often frozen at the earlier design cycles. Whereas on the right side in green, we have the CSI-2 over C-PHY, again using 18 SoC high-speed pins. And here, we are able to support not only the by 4 by 1 equivalent sensor, but also a whole gamut of additional permutations of sensors, mainly because the definition of a port, it may be mapped to essentially a lane deskew mechanism within the SoC. And we have the CSI-2 over C-PHY channel rates. For standard, it is 6 gigasymbols per second or 13.7 gigabits per second. And for short channel, it's an 8 gigasymbols per second or 18.3 gigasymbols per second. I should note everything on the slide. It is mapped to what's available today, the 16B over 7S. Latency reduction, transport efficiency, it helps to dynamically improve sensor aggregation. We did an in-depth analysis of automotive imaging system using CSI-2 over C-PHY 16B7S. And what we observed through that in-depth analysis are that the multi-sensor aggregation using the off-the-shelf 2.3 megapixel sensor, and if we configure them as 12 bits per pixel at 60 FPS, just by enabling the LRT packet delimiter quick, which is a highly optimized way of representing the EOT, LPS, SOT delimiters, and particularly in C-PHY, it is incredibly efficient just by using a single symbol word control code. We were able to realize just by enabling that LRT PDQ reduction of energy consumption by around 23%, or conversely using the same network and supporting 40% more sensors, just using that example. So this is a very highly popular feature. It has gained a lot of traction and deployment across multiple platforms. LRT also supports an ALP mode in which there's a pathway to help alleviate the need for dual voltage signaling, which has a number of benefits from alleviating current leakage, electrical overstress that may result from transistor stacking. USL builds on the LRTE, and the primary objective of the USL is to help reduce the number of wires from a Mipi camera module to an SoC, facilitate replay protection, encapsulation, and inheritance. And from the USL perspective, C-PHY in particular is already supporting, the 16B7S solution is already supporting fast bus turnaround. And more importantly, we are going to be discussing what are the fast BTA durations in the upcoming camera interest group call on December 4th. If we look at the system integrator OEM requests for what may be an ideal conduit solution for client product platforms, perhaps even robotics, the ability to traverse a longer reach, such as say around 36 inches, and a total channel loss of maybe around 24 to 31 dB channel loss, facilitating data rates up to 5 gigabits per second for 4K video transport, were some of the preliminary considerations behind what is depicted in this slide as a 3-wire CSI-2 over C-PHY 16B7S solution. Architecture A and B are using transitionary, are labeled as transitionary solutions, where the camera module may use the existing legacy sensors coupled with the translator bridge that is a C-PHY 16B7S using the USL fast BTA capability to reduce the entire wire count to just 3 wires, and ability to switch between architecture A and architecture B, where the translator in architecture B has an integrated ISP, may provide the necessary permutations of realizing degrees of image quality across entry-level, mainstream, and premium tier platforms, while still maintaining the same chassis constraints and configurations. Taking the architecture A and B from the prior slides and merging them as integrated solution is depicted in this slide as architecture C and D. Again, one of the important benefits and one of the standard features of C-PHY across the industry are the incredibly low energy consumption at the transmitter level, channel, and the receiver. Specifically, as what George mentioned, the ability to transport 16 bits over 7 symbols helps reduce the toggle rate by a factor of 2.28. So with that, I would like to welcome George to discuss the upcoming C-PHY developments.
Hi, so I'll describe what's up and coming in C-PHY and what the C-PHY working group is spending their time developing now. So we're actually working on a new backward compatible mode where instead of translating 16 bits into 7 symbols, there's a new C-PHY 3.0 uses a multi-level coding technique where 32 bits can be translated into 9 symbols. So that actually results in a much higher coding efficiency, more bits per symbol, which has a lot of advantages. So simulations also, show that the emissions are lower. There is a modification to the encoding, the coding, the mapping functions, and also the calibration. However, this still operates over the same 3 wires and is it's in a lot of ways very, a lot of things are very similar to the existing mode. You can see on the right there's a diagram showing the upper figure is showing it looks like 3 sine waves superimposed. This is showing the levels, the single-ended and the differential levels that exist on the lines of a lane for the 6 different states of C-PHY 2.1. Now, going to C-PHY 3.0, 3.0 is supporting now a mode where there are, instead of 6 states, there are actually 18 states. And that can be accomplished by actually outdriving more, an increased number of levels from the transmitter, and then at the receiver to be able to receive the more differential levels. So it looks like there are a very large number of different levels transmitted, and it's not necessary to receive to differentiate between all different 18 levels. There are actually only 4 different amplitudes that need to be recovered at the receiver. Just as with C-PHY 2.1, there are 3 different single-ended levels transmitted, but with C-PHY 2.1, there's only each of the differential receivers only needs to determine whether the signal is above or below 0. And you can see in the bottom diagram, there's showing the triggered eye diagram of C-PHY 3.0, where there are 3 different eyes rather than just a single central eye. There are in this diagram, you can also observe there are some barely open eyes above the 3 central eyes. It's actually not necessary to decode those at the receiver. It's only necessary to pick up the 3 central eyes. So this has the advantages here are that now it has a higher throughput for one thing because of the multiple levels, and it also in C-PHY 3.0 there's some other features that are included too. There's improved margins for the advanced low power mode. There are some enhancements to the built-in test capability, and also we're developing some application notes to kind of in tandem with the specification. So there are actually some Verilog implementations of the mapping and coding that we're going to be releasing. This actually comes for this is for both the C-PHY 2.1 for the 16B7S and also for the 32B9S modes. There's an interconnect guidelines application note. And also we're working on some channel models for those are actually already released, the channel models, but also some extended channels for other compute applications as well. I think that's that's a brief summary of the highlights of C-PHY 3.0.
Thank you, George. You are welcome to stay on the.
Oh, okay. Thanks.
We are about wrapping this up, and we have some very good questions for you too, George. Right. So from summary, CSI-2 protocol, we had the first mover advantage with the smartphones using PHY solutions such as C-PHY and D-PHY, and we continue to advance for beyond mobile product platforms. Leveraging the established infrastructure, CSI-2 or C-PHY imaging conduit solution is broadly used by camera sensors targeting broad range of applications across multiple platforms. And as we hear from George today, the solution continues on evolving to explore pathways to reducing energy, facilitating high performance sensors. Within Mipi, we have the camera interest group, which is open to adopters and contributing members, and presently exploring the ideal imaging architecture solutions for embedded and non-embedded applications using CSI-2 over C-PHY. Core features and capabilities, including the differential pulse code modulation, latency reduction, transport efficiency, scrambling, MPC, USL, smart region of interest, always on Sentinel Conduit are covered, and deeper explorations of how AOSC and SROI may be used were discussed in today's webinar. The next webinar, which is going to be Wednesday afternoon, today afternoon, will be exploring pathways of realizing superior IQ on client product platforms. With that said, George, I have some very good questions coming from chat window, and some additional questions that came from member companies. The first question, George, is that from a backwards compatibility perspective, is there a pathway of using the 32B9S camera sensors with the 16B7S SoCs, and also the opposite, the 16B7S camera sensors with the 32B9S SoCs on imaging systems?
Oh, thanks. Yeah, good question. Yes, so the upcoming C-PHY v 3.0 spec actually requires that the original 16B7S mode be supported in all devices. So there would then be essentially a mode bit can be toggled in either the image sensor or the SoC, so that if a 32B9S capable image sensor is used with an SoC that doesn't have that capability, then the image sensor can simply be operated in the 16B7S mode. And the opposite is also true. So that so the devices can always communicate with each other.
George, physically, after all, they are using the same 3 pins or 3 wires.
Yes, both modes use the same 3 wires, and yes, and the spec is written in a way that always requires the 16B7S mode with all of its electrical specs are required in all devices. So that base mode is always present.
Great. Thanks, George. That's super helpful for system integrators. The second relatively important question, George, is that like 16B7S was already targeting pathways of reducing energy for imaging systems with a 2.28 effective coding gain. Transitioning into 32B9S signaling solution, can you comment on if it is actually helping to improve the overall energy consumption, and from a system perspective, including the channel transmitters and the receivers on imaging systems?
Okay, yeah, thanks. Yes, actually, so we can confirm that. So with the operating, if you compare the highest speed capability of the 32B9S to the highest speed capability of the 16B7S, the energy per bit of 32B9S is lower. And in fact, there is one company that has contributed some test results of test silicon, and it has actually demonstrated that there is less energy per bit with 32B9S. So that's comforting to have that that confirmation from real hardware.
George, these test results are available for Mipi member companies?
For contributor members, yes, they're available in the Mipi Causeway for contributor members. Yes.
Okay.
It's a good reason to be a contributor member. Yeah.
We have a good question from Rajesh on the chat. In yesterday's webinar, there was a discussion of CSI-2 over D-PHY ECM, and Rajesh is asking, how does D-PHY ECM, is there a pathway for D-PHY ECM and C-PHY to coexist?
I think so. So just as right now, there is a capability to build a dual mode PHY. The electrical interface is really, there are really no differences in the electrical interface. So I believe pin sharing should be, the considerations would be the same. The only thing that would be different are the other functions within each PHY. So the C-PHY mapping and coding versus the D-PHY ECM embedded clocking. Those are kind of behind the pins, so to speak. So I believe those functions should be able to coexist. Yes. So I think there's a pathway for that.
That is also highly encouraging, George. Yeah. We have another question from Koichi. How many signal levels are transmitted by C-PHY version 3.0 transmitter? Looks like 7 signal levels on the figure.
Yes, so there are actually, yes, so it's 0, so from 0/6 to 6/6. So that's true. There are actually 7 levels, that are produced by the transmitter, and that actually results in, I think, a few more at the receiver. Those are actually, there's a very straightforward way to produce those levels, and in fact, there's an example in the spec drafts right now of a transmitter of a driver to produce the 6 levels.
All right.
Mm-hmm.
George, thank you so much for this incredibly informative presentation on how Mipi CSI-2 over C-PHY has already solved number of engineering challenges for imaging systems, but also continues to evolve with the C-PHY 3.0 with the 32B9S solution, which is highly encouraging. I would also like to note for the audience, if you have any subsequent questions, please don't hesitate to send them to cig@mipi.org. That's Camera Interest Group at mipi.org. And I would also remind that this presentation with George Wiley was the second of the 3 webinars of this week. And we have the 3rd webinar today, Wednesday afternoon Pacific time, with Suyang Zhang on how to best realize superior image quality using Mipi interfaces on the Lenovo ThinkPad notebooks. With that, George, thank you. And also everyone in the call, thank you so much for your participation.
Great. Thanks for sharing the opportunity to talk about C-PHY and imaging applications. Appreciate that. Thanks.
Of course. Bye, guys.